Welcome back to Freeburg's Free Advice. Thanks for tuning in. I've been working on some rational functions with my tutoring kids the past week or so. I wanted to put one of these up here for you guys so that you can reference it and or forward on to your friends if they're still stuck and want to take another look at these. So let's take a look. So in general, rational functions are when you have a polynomial on top and on bottom of some fraction. So we've got this division piece going on, which is going to create a restricted domain because we don't want to divide by 0. And that's what's going to ultimately create these vertical asymptotes. So first thing I want us to kind of take a look at is the idea that if I'm in the denominator and I create a 0 here, if it's 0, this is going to create our vertical asymptotes. Okay? And then that's one of our key pieces, right? So that's that vertical piece we can never ever cross. One of the other asymptotes we're going to look at is this idea of a horizontal asymptote or a slant asymptote, and that's basically what's going to happen in the limits, in the extremes, as we approach the infinities. So most of the time what you guys are going to be dealing with, at least in the pre-calc class I've been working, you may see a slant asymptote, but for the most part you're going to see these horizontals. What you're looking at is just these lead coefficients. So if I focus just on the highest degree, that's what's important, because as we get out towards infinity, or even let's just say a billion squared is so much larger than a billion or 6 that we ignore it. Same idea, a billion to the 4th power is so much larger than a billion to the 3rd or a billion squared, so we just kind of ignore these in the extremes. So what's going to happen is we approach this x squared over x to the 4th, which we know from our exponent rules means we're approaching 1 over x squared. And so if you were to throw in a billion there, that means you get 1 over a really big number, which means we're realistically approaching 0 in this case. Okay? Other situations is you could have the same degree on top and bottom. So let's say I had a situation where it was x cubed over x cubed, or even more generically, let's say it was some ax cubed over bx cubed. Okay? Well, and you've got all these other things that we can ignore, right? Well, what happens is those x cubes cancel, right? So that's just 1. Well, we would approach 1 other than if we have coefficients you want to take a look at. Okay, in this case, I'm going to approach a over b. So if it was truly just x cubed over x cubed, we'd approach 1. But let's say it was something like 3x cubed over 2x cubed. You would approach 3 over 2. Okay, so that'll help you find these horizontal asymptotes. The next thing we look at is we want to figure out what the X-Intercepts are. And so we know that if I throw in a 0 for y, that's going to create an X-Intercept. And so when I throw in a 0 and I multiply by the denominator, essentially what's going to happen is if this is 0 and I multiply both sides by the denominator, that denominator just gets completely wiped out. Okay? Because 0 times anything is 0. So what you're actually looking for then is just the zeros of the top. Okay? So if we make the top equal to 0, we're going to be able to find our x-intercepts. Okay? And then, as we know, if we throw in 0 for x, so that becomes a 0, that becomes a 0, that becomes a 0. Okay? All those get canceled out, and so in this case, I would see I have negative 6 over 0. Okay, well, what is negative 6 over 0? It's undefined. And so we see that in this particular case, we actually don't have a y-intercept. And so in this case, we won't have a y-intercept, partly because we're going to have this vertical asymptote at x equals 0, which is our y-axis, so that's why that would make sense. Okay, and we'll talk about that here more in a second. So normally, though, you just throw in 0 and you may end up with like negative 6, and let's pretend these x squareds were here. Negative 6 over negative 12, so we'd see that our y-intercept was negative 1/2. Okay, so you know how to find x-intercepts, you know how to find y-intercepts, but I think when you look in this format, the two new pieces are going to be our vertical asymptotes, so the 0 at the bottom, can't divide by 0. Horizontal asymptotes, what happens in the extreme, so looking at those most dominant degreed terms, and where does this head towards the infinities, okay? So, with that knowledge there, let's start fresh and actually figure this out. So, one of the things you want to do first, because we're finding zeros, is let's go ahead and factor. So on the top, we see that this can factor into x minus 3 times x plus 2. And so that helps us find zeros easily. Okay, in the bottom, okay, I'm going to actually switch up colors on us so we can kind of stay color coordinated. In the bottom, I see that there's an x squared that's common, so we can pull that out. And then I'm just left with the x squared plus 4x minus 12. So that's factorable as x plus 6 and x minus 2. Okay. So here we have it all factored out. This is going to help us when we find things. So let's think about the vertical asymptote right now. We don't want the bottom to equal 0. So my vertical asymptotes are going to be at x equals 0. Okay, because of this one. And I like to make a little note that has a multiplicity of 2. Okay, because that's going to change the behavior. Okay, because the multiplicities tell me, do I have opposites and sign change on those end behaviors either side of the asymptote, or do they have the same side? Okay, kind of making that volcano or valley. And then as we look at this one here, I'd see that x is going to equal negative 6. And as we look at this one, we'll see that x equals positive 2. Both of these having multiplicity of 1. Okay, so I am going to have sign change here. Alright, then, because I've already factored at the top, I like to jump to my x-intercepts. So my x-intercepts in this case are going to be the zeros at the top. And so I see that x is going to equal 3 to create a 0. So I've got 3 comma 0. And then x is going to equal negative 2 to create a 0. So there's my 2 x-intercepts. Okay. Next piece, I want to look at the lead coefficients again. So in this case, we already kind of talked about it, but x squared over x to the 4th means that my horizontal asymptote is going to be y equals 0. Okay, so now I've got that horizontal asymptote. Last piece we needed to look at, which we've also kind of already talked about in this example, is I'm going to get a negative 6 over 0. And so my y-intercept in this case is undefined or does not exist. Okay, so there's the 4 key pieces of information we need. Okay, and then I'll show you a second example where there might be a 5th piece, okay, but not applicable in this one. So let's go ahead and actually use this information to help us graph. Okay, so if I jump over to a graph, let's go ahead and build ourselves our graph. Super rough sketch, sorry. Okay, and so our important information, I always start with the vertical asymptote, so we're going to be at 0, negative 6, and 2. So at 0, I've got this vertical asymptote. And I like to show my asymptotes by a dashed line. Negative 6, 1, 2, 3, 4, 5, 6. Okay, so here's another one of our vertical asymptotes. And 2. Alright, so that kind of splits us into almost 4 pieces at this point. Let's go ahead and look at the x-intercepts. X-intercepts were at 3 and negative 2. So I've got an x-intercept here at 3 and negative 2. Note that both those had multiplicities of 1, which means we're going to go through the axis. And then we had a horizontal asymptote at 0. And then our y-intercept is undefined. And so in this particular case, it's actually going to be kind of difficult for us to figure out where to go because all the points we have are on intercepts. So that makes life a little bit more difficult. But let's go ahead and figure out what would you do in this situation. Well, most of you are going to say, I'm going to type in the calculator and see what the picture shows me. You can use your calculator on the test. Awesome. Go ahead and do it. Otherwise, one of the things I like to do is find one more point. Okay, and so I'm going to go figure out that if I plugged in 1 for x, it was going to put me in that other coordinate there. And see where it goes. So if x is 1, we're going to see that we'll end up with 1 squared minus 1 minus 6 over 1 to the 4th plus 4 times 1 cubed minus 12 times 1. And so we're going to end up with 1 minus 7, which would give us negative 6, over 1 minus 4 is negative 3, minus 12 more is negative 15. The good news is that this becomes a positive 6/15, or you could reduce that into 2/5. Divide both top and bottom by 3. So if I got positive 2/5 for that coordinate point, that tells me that it's going to be somewhere here. Okay, and that's actually going to be enough information to help me start my picture. Okay, so as I look at this now, I see that this piece is a coordinate point, and I can't go down, okay, because I don't have an X-intercept there. So I'm going to get forced back up here at this asymptote. Okay, same idea as I go towards the left. It's going to force me up at this asymptote. And then that piece is going to let me use all the multiplicities of our asymptotes to actually graph the rest. So here at x equals 2 at a multiplicity 1, so we have a sign change, means I start down here. And then I know that multiplicity of 1 at my intercept means I go through it. Well, this thing has to eventually approach the horizontal asymptote in the extreme, so it's got a little bit of a bend like this. Now let's think about x equals 0. That had the multiplicity of 2, so that there was not a sign change, so that starts up top. And then we can come through. Again, multiplicity of 1 at the intercept means I'm going to cross through. There's no place for me to turn back up, so I get forced towards the bottom here. And then a multiplicity of 1 at x equals negative 6 means I have a sign change. And so I end up with a graph that looks kind of like that. Okay? I gave you kind of a complex example there, but if you can figure that out, you can figure out almost all the ones that you guys are going to be graphing. Okay? Last example I want to show you guys today is going to be something that has a hole in it. So some of you are like, oh, hey, sweet, there's a rational function. What's this going to look like? Well, let's take the same traits we've been doing. So I want to factor the top. Factor in the top. Oh, no. That doesn't look like an easy one to factor. So what do we get to do? Go back to your old school favorite friend, synthetic division. So we've got 1x cubed, 0x squared, negative 7x, plus 6. And then as we run through our synthetic division, we always like to try 1 and negative 1 first. Again, the trick, if I were to just throw 1 in here, I'd get 1 plus 6 is 7, minus 7 is 0. So I know this one's going to work, plus I built the problem. So I get 1 and 1 and 1 and 1 and negative 6 and 0. Yay! And again, once I know that this works, I like to remind myself I have the factor x minus 1. Now this is just a quadratic, which is also factorable, so this is going to become x plus 3, x minus 2. Okay. And now I've got the top factored. So let's rewrite the top. Top now is going to be our x plus 3 and our x minus 2 and our x minus 1. All over x minus 1. Anybody notice something? Yep, that cancels with that. That is the action that creates a hole. Okay? And a hole means I have an undefined moment because I can't divide by 0. But everything that's happening here gets canceled out by this, so it essentially disappears. So what we're going to see is, for graphing purposes, we're actually going to be graphing this function, I'm going to call it f of x, because we're looking at g of x, is going to be just this remaining piece, this x plus 3 times x minus 2. So even though we were expecting this to have asymptotes and crazy things and look kind of like that last picture, since the whole denominator cancels with part of the numerator, we're actually left with just a quadratic function. This thing's going to look like a parabola. So let's go find the same things we want. In this case, we don't have a vertical asymptote, we have a hole. Okay, so my hole is going to occur at x equals 1. And so what's important for that is we should go ahead and find f of 1 so we know where the actual hole occurs at. And so this is going to give us 1 plus 3, 1 minus 2, and so this will be 4 times negative 1. And so we'll see that f of 1 equals negative 4, and we see our hole occurs at 1 comma negative 4. Yay! That's good news for us. So now we know where the hole actually is. Okay, we have X-Intercepts. Okay, X-Intercepts, just like we've been finding from previous polynomials and stuff, we see that x is going to be negative 3, or x is going to be positive 2. We don't have a horizontal asymptote. Our extremes here, because it's behaving like a parabola, end behavior is going to be up and up, so we could think about the end behavior if we wanted to. Okay, so this is going to be up to up because it has the even degree of the function. We're just a quadratic. This is just x squared plus stuff. Okay, and so last piece is we could find the y-intercept, which would be plug in 0. So we get 3 times negative 2. So the y-intercept is going to be at 0, negative 6. Cool. Let's go plot this now. I'm going to actually use the line function this time. So here's our graph. I've got x-intercepts at 2 and negative 3. I had a y-intercept at negative 6. 1, 2, 3, 4, 6. I knew I had a hole at 1, negative 4, so a hole is going to, I always graph it as literally just a hole, an open circle. And if we kind of looked at it, I mean, if we use the other graphing techniques, because this is a parabola, right, we're going to look at the idea of our remaining function here is x squared plus x minus 6, right? And we saw that from the synthetic division step there. Okay, if we used our negative b over 2a to help us find a axis of symmetry, we'd see that we'd have negative 1 over 2. So as we expect from this picture, somewhere around here, okay, there's going to be our vertex, and then we have this axis of symmetry. So this is going to be a reflection point. This would be a reflection point, and this is enough information to help us graph. So I'm just going to get us a rough sketch. Okay, it goes through the hole, and again, it's just a parabola, and same idea over here. So as we would expect, because that x minus 1 on top and bottom canceled, we're left with a parabola. The only thing is we have this hole. This is an undefined moment from the original function, and that's going to be your function. Okay, hope you guys enjoyed. Thank you for watching Freeburg's Free Advice. Good luck on all your finals this week, and I will see you guys soon. Take care.